Good afternoon, everyone. I welcome all the attendees for our QCrete webinar 24 on influence of aggregates on properties of concrete by Dr. Nagendra sir. Dr. Nagendra sir is having about 36 years of experience after his civil engineering degree, including 12 years as a lecturer. He is a member of CED 2.2 Committee of Bureau of Indian Standards. He worked as technical director at Civilite Technoclinic Private Limited and also Bureau Veritas India Private Limited. Currently, he is working as senior director at Stredden Technoclinic Private Limited, Bangalore. He holds PhD degree in civil engineering with specialization in self-compacting concrete. Now I request Dr. Nagendra sir to share his knowledge on the concrete. Thank you, sir.
Thank you very much, Ashwarya, for the introduction. I hope I am audible to all.
Yes, sir, you're audible.
Thank you very much. First of all, let me take this opportunity to thank the organizer of this presentation for giving me an opportunity to share whatever the knowledge we have gained over the years with so many organizations, and also in charge of the laboratories in South India as well as some of the laboratories in North India when I was working with Bureau Veritas India Private Limited. And today, the topic of discussion is influence of aggregates on properties of concrete. I represent a company called Trivandrum Technical Private Limited, which has got its offices in Bengaluru and in Hyderabad. We are in the consultancy in civil engineering. We have been doing testing of building materials and non-destructive testing of structures, both RCC as well as steel, geotechnical investigations, design review, proof checking, and design of structures, and QA in construction. With this portfolio, we are working, starting this organization in 2017. Earlier, as told by Ashwarya, I worked with Bureau Veritas in Sweden. Now, in this presentation on influence of aggregates and properties of concrete, hello? The aggregate, as you know, occupies about 70 to 75% of the volume of concrete. So its quality is of great importance. When so much volume is occupied by aggregates, the volume, by so much volume, we need to look into the qualities of such material. Aggregates may affect the following properties of concrete. One is strength of the concrete, second one is durability of the concrete, and third one is structural performance and economy. Hello? Is it? Yeah, I will do that. Just tell me whether I'm clear or not. Now I will just speak. Okay. Hello.
Yes, sir. Yes, sir. Now it is clear.
Yeah. So as I was discussing, the aggregates which affect various properties of concrete include strength of the concrete, durability of the concrete, and its structural performance and economy of the concrete. Because ultimately, within the aggregate, which decides the economy of the concrete mix. Of course, one important thing I'm going to discuss is also the workability of the concrete. Workability in first stage and all other things in hardened stage. Aggregates have three main functions in concrete. To provide the mass particles which are suitable to resist the action of applied loads and show better durability of the cement base alone. To provide relatively cheap filler for the cement material. To reduce volume changes resulting from setting and hardening process and for moisture changes during drying. So the last one is equally important because the cement base undergoes considerable shrinkage. If you add aggregates to the concrete, if you add aggregates to the cement paste, it helps in reducing the volume changes which happens from setting and hardening process. The moisture changes during drying also results in shrinkage, and aggregates are very good in preventing the shrinkage. So the aggregates have got all these important functions to perform in the concrete. The properties of concrete are affected by the properties of aggregates. That means we need to understand the properties of aggregates very well. I mean, we need to test the aggregates in concrete before we use them in concrete. The mineral character of aggregate affect the strength, durability, and elasticity of concrete. How strong the aggregate is. The mineral character, mineralogy, mineral composition helps the aggregate of the concrete in order to achieve the required strength. The surface characteristics of aggregate affect the workability of fresh mass and the bond between the aggregate and cement based in hardened concrete. If it is rough, workability decreases and bond increases. The surface characteristics are important and we need to understand these surface characteristics very well. Then, the grading of aggregates affect the workability and density and economy. This is the most important aspect of aggregates, the gradation of aggregates. The gradation is very important. We need to understand, we need to check the gradation of aggregates whenever we want to propose aggregate from a particular source. The amount of aggregate in volume of concrete also matters. How much amount of aggregate is present in one unit or 1 cubic meter of concrete. So all these four affects the properties of concrete in a big way. Now, higher the aggregate amount per unit volume of concrete results in less volume changes during setting and hardening of moisture changes. That's already explained. Shrinkage. The shrinkage, cement base shrinks very fast, whereas the aggregate prevents the shrinkage. The aggregate, higher the aggregate volume, there will increase in strength and durability and increase in cost. This particular graph you can see as the aggregate content increases, the shrinkage decreases. So it's a common practice to use as much aggregate as possible in concrete within the practicable limits. So we have to design the concrete mix in such a way to use maximum aggregates in it. Of course, we need to put the use the minimum paste also, without which it will not be possible to achieve the required workability, required durability, and required strength from the durability point of view. However, all aggregates are not inert. We are normally assume the aggregates are inert materials, but some aggregates they have the physical action is swelling and shrinkage. This by the physical action, they may swell and they may shrink. Some aggregates, not all aggregates, lightweight aggregates, things like that. So, the thermal action is another, chemical action is another very important thing because some silica, active reactive silica present in aggregates, reacts with alkalis present in cement, resulting in alkali silica reaction. So the physical action, the chemical action, and the thermal action. Some aggregates are expansive in nature or contraction in nature, not the normal aggregates, of course. These three properties, the physical action, the chemical action, and thermal action are important to understand. Like the other ingredients of concrete, aggregates must also be chosen with certain care to interpret satisfactory concrete. So, let us have a look into various classification methods, how to classify the aggregates. According to its source, the aggregate can be classified as natural aggregates and artificial aggregates. So natural aggregates, as I will know, may be deposits with no change in their natural state other than washing, crushing, and boiling. It remains same. It's a natural available material. It can be sand, it can be gravel, it can be crushed stone from the stone crushers. Artificial aggregates were obtained either as byproduct or by a special manufacturing process such as heating. So the classic examples are blast furnace slab. Class furnace can be used as both fine aggregate as well as coarse aggregate. So this is expanded further is another example which comes from as a byproduct from the heating. According to another classification is petrological classification. According to the origin, the aggregates maybe of igneous rocks origin, maybe of sedimentary rocks origin, or metamorphic rocks origin. So, classification is equally important. Then the aggregates don't weight. Some aggregates are lightweight, some aggregates are more normal weight, some aggregates are heavy weight. So normally hematite has got more than 2.8 specific gravity, maybe up to 4 or so. Normal aggregates specific gravity between 2.4 to 2.8. Lightweight aggregates will be having normally specific gravity less than 2.4. Normal weight aggregates, 383, IS 383, which was revised in 2017, 2016, covers most of the common aggregates, whether it is a natural sand, gravel, or precious stone. To produce normal weight aggregate weight concrete, the density is about 2,200 to 2,400 kg per cubic meter. So when it comes to fine aggregate, we all would like to use natural river sand, which is very clean, especially from the river beds. But when this natural river sand is normally becoming very much less, it is decreasing its availability. So because of that, we are resorting to what is called precious stone sand. So you can see the precious stone sand, the normally fine aggregates constitutes about 35 to 35% by volume. So the particles which are less than 5 mm in size are called as fine aggregates. Coarse aggregates again, gravel and precious stone, which are greater than 5 mm, typically between 9.5 mm to 37.5 mm. These are normally used in two sizes. One is 20 mm, another is 12.5 mm. So coarse aggregates plays a very, very important role. So sampling, whenever you want to test the aggregates, because first of all, the aggregates shall conform to the various requirements of ISO. So when you want to test the aggregate before actually using in the laboratory, the sampling plays a very important role. It should be a representative sample. Many times what happens is the aggregates available outside are of very good quality, but the sampling is done in a bad way. So thereby, the result from the laboratory may indicate the aggregate sample doesn't conform to the requirements of ISO. That's why the representative sample must be chosen, must be selected properly by taking various portions. The main sample is made up of portions drawn from different points. The minimum number of portions increment is 10, and they should add up to a weight not less than you can have this figure greater than 25 about 50 kg, 25 to 5 about 25 kg, less than 5 about 13 kg. So like this, you need to select the aggregate, sample it properly before sending to the laboratory. Another way of sampling when it comes to the laboratory is by quality method. Mix the clean sample over 3 times on the lower surface, show them the sample to a conical shape, press the atoms and flatten the conical shape, divide them on the 4 equal patches, discard the 4 diagonally opposite problems and use the remainder. If this remainder is too large, follow the same path once again. So this is how the pattern of aggregate is done for sampling purposes. Then, what we need to understand with respect to aggregate is its shape and surface texture. This is basically the classic example of the origin aggregate is what is made up of, what type of rock characteristics are there. So particle size. What? Don't know. When internet voice notes in a lot of listening yes, ma'am. Okay, so just give me 2 minutes to start again. Yeah. Hello.
Hello.
Am I audible? Am I audible?
Yes, sir. Audible. Yes.
Is it audible now?
Yes, sir. Yes, sir. Audible.
Okay, I will continue. Sorry for that disturbance. As I was mentioning, in addition to the origin of the rocks, the particle shape and surface structure plays a very important role. This is again how the aggregate is produced. Based on that, we can really control the shape and surface structure. In addition to chronological character, the external characteristics, that is shape and surface structure aggregates, are of importance. Particle shape, rounded shape, completely waterworn or fully shaped by attrition, that is river or gravel. Normally, that's why we get river sand, the most popular one. And irregular is partly shaped by attrition, so it contains some rounded edges. So you can see the typical example of flat and elongated and angular and round aggregates of natural origin. Rounded aggregates are suitable to use in concrete because flaky and elongated particles reduce workability, increase water demand, and reduce strength. But in the case of angular particles, the bond between the aggregate particles due to interlocking, but due to higher surface area, angular particles increase the water demand and therefore reduce workability. As a result, for the same cement content and same workability, rounded aggregates give higher strength. So this is how you can see the difference between the rounded aggregate and the angular aggregate. Surface texture again affects the bond to the cement paste, also influences the water demand of the mix. Smooth will give you bond between water paste and aggregate is weak in case of smooth aggregates, whereas in case of a rough aggregate, bond between cement paste and aggregate is strong. Surface structure is not a very important property from the composite system point of view, but aggregate having rough surface structure perform better under structural and tensile stresses. So this is how we can understand the impact of surface structure of aggregate. So you can see the smooth aggregate and also rough aggregate, rough texture aggregate. The next most important aspect of aggregate is the particle size distribution of an aggregate sample. There one is gradation. We call it as grading of aggregates, which we find out from sieve analysis. Strength development of concrete depends on degree of compaction, workability, together with many other factors. So, the satisfactory concrete should be compacted to a maximum density with a reasonable work or the reasonable energy. On the other hand, the weak concrete, all aggregate particles must be covered by cement base. So, this is the essence of compaction. The grading of aggregate must be so that the workability, density, volume stability of concrete may not be adversely affected by it. Fine particles, if you use more and more fine particles in a concrete mix, the cost becomes very high because in order to face each and every particle, the cement requirement increases. As the aggregate size increases, that means that the coarse particle, when you use more and more coarse particles, your cement consumption reduces, but the cost of loss of workability. So fine particles will result in higher cost, whereas coarse particles results in loss of workability. The reasonable combination of fine and coarse aggregate must be used. So this is what the mixed design is all about, or the mixed proportion is all about. First of all, we need to have a good granular aggregates. Then we can combine both fine and coarse aggregates in a proper way, in a suitable proportion, so that you will be able to achieve the mixed design or the properties which you are aiming at, the target properties. This can be expressed by maximum density or minimum rights concept. So this is one concept which is a very popular concept. We have to proportion the coarse and fine aggregates in such a way we will achieve the maximum density with minimum voids. Minimum voids results in minimum use of cement, whereby the economy can be achieved. If you look at this example of about four spheres, the cube kept in four spheres kept in a cube of dimensions 2D by 2D by is filled with the spheres of diameter d. That volume of the cube will be 2D cube. So you can see here the cube. So first sphere, and then we can find out the solid volume of sphere and volume of cube. So volume of sphere, volume of cube, large volume will become 3.8D. So irrespective of the size of the cube, if you same thing, if you really keep more, same cube is filled with the spheres of diameter d by 4, then we'll have nearly about so many spheres. Okay, number of spheres. The solid volume will be same. That means the size of the aggregate is not important. If an aggregate with the same size is used, amount of void will not change. Amount of void volume will not change. So, to overcome this, different sizes of particles should be used. To overcome this, different sizes of particles should be used. However, we should not forget that as aggregate get finer, the surface area increases. We cannot use too many fine aggregates also. If the fine particles increases, there will be again demand for the cement. More surface area, you need more paste and more water requirement. But at the same time, you cannot have more bigger particles also on the same size of the aggregates. So thereby, the importance of gradation comes into picture. So if you look at this figure, it becomes quite clear. In the first jar, we have same size of aggregates. In the second jar, again same size of aggregates. But if you mix both coarse and fine particles together, the reduction in voids takes place. That you can see in the bottom three cylinders. So size really matters, gradation really matters. It should be graded. Factors affecting the desired body. Surface area of aggregate. The lower the surface area, the lesser is the taste requirement. So relative volume of aggregate in concrete. Higher the volume of aggregate, the mix becomes economical. The higher the strength will be higher. Higher volume stability, as I mentioned earlier also, the shrinkage will be less and less workability. Of course, because of when you get the advantage of economy as well as higher strength, workability suffers. But of course, we can take care of the workability by using suitable chemical admixtures. Now, workability, what is workability? The ease with which a concrete mixture can be mixed, transported, placed in the form and compacted without any segregation. Workability increases as the amount of paste, the fine aggregate and dot aggregate, coarse aggregate increases. It also increases the amount of matter between the coarse aggregate particles increases. Segregation. Separation of the particles with different sizes and specific gravities. The requirements of workability and absence of segregation tend to oppose each other. Thus, these two factors are interrelated. The nature of this is workability, which in turn affects most of the properties of concrete. So, workability and segregation needs to be addressed as far as coarse aggregate is concerned. Of course, we are going to again discuss both fine and coarse aggregate from the parameters point of view. Which are the parameters we look at fine aggregates as well as coarse aggregate? Natural sand are naturally prepared from coarse aggregate sand, crushed sand, gravel, or such enough materials conform to highest 2016 shall be used. Which are the tests we conduct on the conduct in the laboratory on the fine aggregates. So these are the tests. One is shear analysis, second one is specific gravity, And what is bulk density? Bulk density is something we really do not give much importance, but bulk density really the advantages are there if you really closely monitor the bulk density of aggregates, both from the road as well as the rest of the use and rather bulking. Bulking of aggregate is of course is important when you are doing the volume pricing. Then organic impurities and fine aggregates should be verified. It will reduce the strength of the concrete. And of course, we have a list of deleterious materials starting from coal and lignite, KOLLAM, materials thinner than 75 micron, soft fragments, shale, salinous test, chemical tests. So these are the tests which you conduct on the fine aggregates. So if you look at the requirements of gradation of aggregates, we use this particular requirement as per IS 383. That is starting from 4.75. Of course, there is 10 mm series also shown here. 4.75 downwards, 4.36 seed, 1.1 seed, 600 micron, 300 micron, and 50 micron. There are four zones of sand: zone 1, zone 2, zone 3, and zone 4. So these each zone and each field, there is a percentage passing requirement is specified in IS 383. Whatever the sample is test, we need to calculate the percentage passing, and then we have to compare those results with this table. So in this table, if you closely observe, any sample, any sand which comes up to 600 micron, besides the 600 micron, whatever the value is there at 600 micron, decides to which zone the fine aggregate belongs to. So 600 micron is a very critical parameter. Percentage passing through 600 micron is critical parameter, and you can see from the close look at the grading limits of fine aggregates, it can be seen that zone 1 is the coarsest and zone 1/4 is the finest. Zone 2 and zone 3 are the moderate zones. So we prefer to have a fine aggregate in the concrete conform to zone 2 and zone 3. Zone 1 can be used, only thing it is coarse in nature. We need to increase the percentage of sand when we want to use zone 1 sand. So these are the few fractions of time. So let us say 4.7, 2.36, 600, 300, 1.18, and then we have 150 microns and time like that. In addition to this same analysis of the gradation, we also look into what is called as materials finer than 75 micron, or it is called as silt content if it is a natural river sand. If it is a precious stone sand, it should be called as a particles materials finer than 75 micron. And the method we adopt for finding out the silt content or the particles finer than 75 micron is by washing method. We need to adopt the washing method. We cannot use the dry method, dry sieving method, because the particles get adhered to the sieves. When the particles get adhered to the sieves, we won't be able to get the correct picture of particles passing finer than 75 micron. So this test is very important, especially whether it is a natural river sand or whether it is a precious stone. Because in precious stone sand, normally will have more fines in it passing through 75 micron. We need to control these fines. These fines value may go up to even 20%. So if you look at this table, these values are about 3% and 15%. For 3% for a natural river sand, maximum of 3% for a natural river sand, and maximum of perfect stone sand. Now, after understanding these requirements of a frame aggregate which affect the properties of concrete, let us look into coarse aggregates. Coarse aggregates are also tested for these properties, specific gravity, bulk density, loose and rotted bulk density, water absorption, flakiness index, elongation index, gradient impact value, abrasion resistance, crushing value, alkali aggregate reactivity, and soundness. Of all these things, first four are important from the building construction point of view, and the remaining are also equally important. But normally in road constructions, we look at Aggregate impact value, operation resistance, accurate crushing value, these are the important tests from the road construction point of view. Of course, equally aggregate reactivity is something which you need to verify before you accept the aggregate sample from a particular source. Because we do not know, some of the aggregates may have some reactivity in the silica present in aggregate may react with alkalis present in cement. Specificity is the most important parameter as far as both aggregates are concerned. There is a portion from the road. Specificity is the ratio of the weight of the unit volume of the material to the weight of the same volume of water at 20 degrees to 25 degrees Celsius. So you can determine like this weight of the aggregate and the weight of an equal volume of water. And specificity is specifically based in mix design to find out the material. Weighing its the weight. If you fix the weight, you can find out the volume. Okay, that is for the conversion of the specific use, and also for proportion the concrete mixes from the absolute volume method with measures of the specific variety. Also, again, that is not a measure of quality of aggregate. But of course, also we can say higher the specific gravity, better is the aggregate, because normally our granite aggregate has a specific gravity about 2.6 or so, whereas the hematite and the other aggregates do have a specific gravity of very still higher values. Then coming to acceptance criteria given in various IS3 classes for aggregate impact value, as I told you, these are important from the bearing surfaces point of view or the road construction surface point of view. 45% for the normal construction and should not be greater than 30% for the bearing surfaces. Then specific gravity values are going to be 2.6 to 2.2. Water absorption is another important property of both coarse and fine aggregates. For coarse aggregate, water absorption will be normally starting from a very low value of 0.2, 0.3, about 0.5% to 1%. And for fine aggregates, it will be up to 2%. This plays a very important role while proportioning the concrete mixers, while determining the water addition to the concrete. Flakiness and elongation index is again indicate the shape of the aggregate. The combined indices, combined flakiness and elongation index shall not be more than 30%. Abrasion resistance is another test which we do using Los Angeles abrasion testing machine. And again, 30% for the road construction purposes and shall not be greater than 50% for other than road surfaces. Crushing value is another important test which says should not be more than 30% for the bearing surfaces and about 50. Suppose if the value of crushing increase of more than 30%, the aggregate to be used in concrete other than bearing surfaces. In case aggregate crushing value exceeds 30%, then the test for 10% fines has to be done, and the minimum load for the 10% fines should be 50 kN. So this is how we can accept the coarse aggregate if it is not conforming to crushing value test. Then IS 2386 various parts gives the method of test, how to carry out the test as per the standards, what are the equipments required, how to sample the aggregates. So these are all the things given in IS 2430 for the sampling, and 2386 part 1 to 7 gives the procedure for carrying out the test. Now, determination of grading the aggregate, these are the two different methods. One is fineness modulus, another is granulometry or sieve analysis. Already I told you about this. The grading of particles of an aggregate sample is performed by sieve analysis. The sieve analysis is conducted by the use of standard test sieves. Test sieves have square openings and their designations correspond to the size of these openings. Fineness modulus is determined again from sieve analysis only. It is the sum of the cumulative sum of the cumulative return on each sieve divided by 100. For fine aggregate, the practical limits of sieve analysis are between 2 to 3.5, and for coarse aggregates it may be from 5.5 to 8. So these are the two fineness modulus values. So fineness modulus is not always representative of the gradation of an aggregate sample, and various gradation curves may give same fineness modulus. So fineness modulus might be sometimes misleading. So you should be careful while using the fineness modulus for any practical purposes. The gradation curves, the vertical axis represents the percentage passing, the horizontal axis represents the sieve opening. So these are the set of sieves, these are the sieve fractions on 20 mm, 12.4 mm, 10 mm, and 4.75 mm. And for coarse aggregate, for various maximum size of aggregate, 40 mm, 20 mm, and 12.4 mm, the percentage passing ranges have been given on each size, sieve sizes. 40 mm size, 20 mm size, 12 and 12.5, 10, 4.75. So these requirements are very important. We have to see that these requirements are met. As I told you, normally 20 mm aggregates conform to single size requirements, and 40 mm aggregates, sorry, 12.5 aggregates conforms to graded requirements. We need to blend 20 and 12.5 mm in suitable proportions to get graded 20 mm size aggregates. So always blending is necessary to get good gradation of the aggregates. Otherwise, it becomes single size aggregates. Here also, like fine aggregates, you can verify the particles finer than 75 micron, which shall not be more than 3% for the uncrushed aggregates, and for the crushed aggregates, it should not be more than 3%. Then thickness gauge is used to measure the flakiness index of the coarse aggregates. So this test is also very important, and we need to carry out this test as per the procedure given in the standard. Then length gauge is for the elongation index. Then combined flakiness and elongation indices shall not be more than 30%. Earlier it was 24%, and now it increased to 30%. And also in nowadays, IS 380 is allowed up to 40%. So it's the Los Angeles separation testing machine, which we normally use to find out the Los Angeles separation value. And in the pressure test, or the test bonding in the pressure testing machine. The volume, these are the tests which we conduct. So now, coming to the moisture condition of the aggregates. Four moisture conditions are now can be seen. One is wet and dry, another is very dry, second is surface, saturated dry, and fourth one is wet condition. So each condition has to be ascertained properly in order to find out the water requirement for the coarse aggregates while mixing the concrete. Then bulk density, the rate of the aggregate that will fill the unit volume, unit weight depends on its size distribution, shape of the particles, and the compaction method we arrived. So based on these three important characteristics of aggregate, that is gradation, shape, and the effort, the compaction effort, what type of effort you are doing, whether it is a loose compaction or a heavy compaction or added compaction. So depending upon that, the bulk density value changes. Moisture content, especially for fine aggregate, the optimal working content packing efficiency increases. So this is the thing which you need to understand. Unit weight, it can be loose unit weight or compacted unit weight. You can measure it by a standard method. Another important aspect of fine aggregate is bulking of sand. Some sand, when it comes in contact with moisture, the volume increases. Thereby, the apparent volume will be more, whereas the actual volume, actual weight will be less. We need to make the correction for moisture content as well as the volume correction when we are using the high volume method. Otherwise, for the weighing method, when we have to estimate the moisture present in the sand so that we can reduce the water content to be added to the mix. So moisture condition of aggregates also will be wet and dry, air dry, saturated surface dry, SSD, and damp wet. So total moisture we need to calculate taking into account of all these things. Alkali aggregate reactivity, already I told you, it's a reaction between the active mineral constituents of some aggregates, and the sodium and potassium alkali hydroxides and calcium hydroxide in the concrete. So there are two types of alkali aggregate reaction. One is alkali silica reaction, we call it as ASR, and another is alkali carbonate reaction. In case of limestone, the carbonate reaction takes place, that is called as ACR. We need to really look into, depending upon the source of the aggregate, we have to do all this test. So alkali carbonate reaction is again, as I told you, happens only if the aggregate is of limestone origin. So we have to alkali silica can be there in normal aggregate also. Check these things. There are 2 or 3 methods for finding out the alkali aggregativity. One is a chemical method, another is marker bar method, which is done in the laboratory, and this chemical method is, of course, an indication of the presence of reactive silica in the aggregate, whereas the marker bar method is a physical method wherein you will be able to find out the expansion in the if at all if it happens, that is not good for the concrete. So these are the pictures you can see where the alkali silica reaction is taking place. The typical cracks, how they develop, visual symptoms, the network of cracks, closed or spalled joints, then relative displacements can also takes place. This takes place over a period of time, and it needs really some conditions to occur. That is alkali hydroxide reactive silica gel reaction product. So this is how ASR can take place. What are the influencing factors? Reactive forms of silica in the aggregate, reactive forms of silica present in the aggregate, which will come to know only through petrography examination. High alkali pore solution is also responsible, and sufficient moisture. Sufficient moisture is present, then only alkali silica reaction can take place. If one of these conditions is absent, ASR will not occur. So all the 3 things. One is high alkali pore solution, then how it will come? It may come through cement also. So cement containing alkalis and aggregate containing reactive silica, and the third one is sufficient moisture. So in the presence of these 3, only alkali silica reaction can take place. So IS 383 gives elaborate procedure for alkali silica reaction and marker bar methods. The marker bar method is also given in 383 as well as in ASTM standard. Chemical method is also given in ASTM as well as in AS 383 method. Petrograph examination is really important to know the mineralogical composition of the aggregate, so that whether it contains any reactive silica or the clay particles in the coarse aggregates. Then we can, by accelerated method, by rapid marker bar method, we can also find the alkali silica reaction. Concrete prism test is important because all other tests are done on mortar samples, whereas concrete prism test is one test which is done using the concrete sample, so that will be more realistic and more useful test to find out the alkali silica reaction. How to control alkali silica reaction? Non-reactive aggregates you should use, supplementary cementing materials or blended cements you should adopt, and limit alkalis in cement. Lithium-based admixtures can be used. Limestone sweetening, that is 30% replacement of reactive aggregate with crushed limestone. So this is how we can control the alkali silica reaction. So these are some of the effects of supplementary cementing materials on ASR. So you can really reduce as you use the fly ash as this percentage of slag and silica fume. So the expansion goes below. The broad line, 0.1% is the expansion value. So when you use all these other things, you can see that the expansion reduces due to alkali silica reaction. Now, we talk about all these parameters or properties, it should be good and all. Then how do you really get a good quality of aggregates? The production of aggregate is very important, is very critical. There are many types of pressures. How do you produce the aggregate? There are many types of crushers available, and these crushers can be classified as jaw crushers, cone crushers, vertical shaft impact crushers. So these are the three types of crushers which are normally produced aggregates in the industry. So VSA aggregates are produced by Wacom principle. Need to study the effect of aggregates from VSA crushers. Fine aggregates from natural sources becoming scarce, costly, restrictions on quarrying from river beds, construction industries to look for alternative sources. That's why sand has become very popular because of the non-availability of river sand. Manufactured sand is one such alternative and is replacing river sand rapidly. VSA crusher has revolutionized the crusher industry. So crusher industry today can produce very good quality, great coarse aggregates as well as finer grades because of this VSA crushing. You can see the status of VSA crushing. We have a bulk rock quarry. Primary crushing of rocks is one stage. We have a crushing plant and production of aggregates. So there are three core stages of this fraction separation, sea separation. So these are the jaw pressure aggregates which you can see they are flaky, elongated, and whereas VSA pressure aggregates are VSA pressure aggregates are typical in nature and they will be having excellent properties with respect to this thing. So we need to understand these VSA pressures very well. Pressure stone sand, sand is defined as a purpose-made sand. Pressure from aggregate produced from suitable source material in VSA pressure. VSA aggregates are ideally suited for production of normal concrete as well as self-constructing concrete. Now, once we improve the quality of aggregate by production method, that is VSA aggregate method, we can really do the optimization of aggregates, optimization of aggregates using packing density. Because if we can select the aggregates in such a way, we get the highest packing density. What is the advantage of this highest packing density? Higher the packing density, lower will be the yards. Lower yards are there, your paste, cement paste required will be less. So we can achieve the economy in cement. At the same time, we cannot use a harsh mix going on the basis of packing density. You need slightly more than the page as required by the packing density method or optimal density method. So we can optimize the aggregates by finding out the packing density, which is defined as bulk density divided by specific gravity. So therefore, it is essential to determine bulk density of combined aggregates. We need to find out the combined bulk density, not bulk density of coarse aggregate and plain aggregate alone. We need to find out both in base state as well as in product condition. So what we can do, if you want to really achieve a good packing density of aggregates, optimization of coarse aggregate of two sizes, first you have to do KOLLAM and control film and control, because we don't get any mixed aggregates. We always get from the crusher single size aggregate from the to blend front and and optimize them through the bulk density method. In the second stage, whatever you have optimized in the first stage of containment go for the optimization with the plain aggregate also, combined aggregate that is. So there also you will find out loose and product bulk densities. So we know the procedure very well and we know to explain bulk density can be measured with a cylinder having known volume. We have to go 20 strokes and fill it up in 3 layers, and we can see that we will get the required bulk density in radial condition as well as in loose condition. So loose bulk density measure shall be filled with wave simply putting it up and again measuring the weight and the volume. Weight by volume will give the loose density. So then fine aggregates. Again, there are two types of fine aggregates. We can combine packing density. We can measure with the river sand as well as with the sand. So in particular study, we studied some of the three ways of pressures, taking the fine aggregates from three different pressures. And again, there are done the the C1 was done for these three crushers, and also requirement is shown here. Materials further than 75 micron was measured, and specified the water absorption, loose bulk density, rapid bulk density, all these things were measured. So this is how the gradation looks like for the natural river sand as well for the various sand obtained from the various crushers. So, as I already explained, this is I told you. Then again, coarse aggregates can be from a bone pressure, jaw pressure, basalt pressure. When we study all the coarse aggregates, we have classified bone aggregate and also coarse aggregates into three: aggregate from the bone pressure, jaw aggregate from the jaw pressure, and aggregate of basalt rock origin. So, of course, again produced from the bone pressure only. And natural river gravel was also taken because river gravel is a very rounded and rounded shape and smooth also it will be. So like this we can combine coarse aggregate and fine aggregate in particular proportions and then these are the again seen as results of containment, type and things like that. Then how do you optimize? Optimization I told you already contain type and how do you vary? You have to go on varying the percentage of from 0% to 100% of an interval of 10%. So you go on increasing the 0% to 10%, and again you can really this is how the bulk density was measured in the laboratory using both coarse aggregate as well as fine aggregate. After optimizing coarse aggregate of 28.1 and then optimization of fine aggregate. So these are the graphs, tables for the 28.1 for finding out the optimum bulk density in those conditions as well as in rapid condition. So coarse aggregate, then combined gradations. We need to do the combined gradations of percentage passing. So you have to do, you can do now. Finally, you have to mix natural river sand and as fine aggregate with the coarse aggregates with various percentage of fine aggregate, 0%, 20%. Like this. So now we arrive at the graph of percentage passing. You can say bulk density versus the percentage of fine aggregate added to the mix. So like this, you can find out the up to the determination of the quantity of aggregates by using mix density. Okay. Now, what is packing density? We can find out the packing density by finding out the volume of each individuals. You can use this particular concept to find out the packing density, and you can also find out aggregate packing factor by dividing the product bulk density by loose bulk density. So finally, what we will be doing is we are interested in finding out the volume of paste required when you find out the optimum packing density. Volume of paste determines how much quantity of cement you have to use. Paste is nothing but water plus cement, or if you are using any other GBBS or fly ash, that also you can see. So volume of paste you can find out, and that is 1 minus bulk density, packing density. Volume of paste is 1 minus packing density. So like this, packing density has to be determined by practical bulk density method, and we can find out the volume of the paste required. Volume of paste calculated above is the content just required to fill up the voids. In fact, some amount of excess paste is always required to achieve self-compactability of concrete. We cannot define self-compactability, otherwise the same paste may be sufficient to get some, let us say 40 mm slump or 60 mm slump, or even for the pumping concrete about 100 mm slump by adding suitable admixture of the required dosages. So you have to increase the paste volume by some amount. Volume of paste calculated above helps in deciding the composition of paste, which includes cement, the ceramic material. It can be fly ash or it can be GGBS, and water and air. Voids in the concrete are in fact either bubbles of entrapped air or spaces left after excess water has been removed. So like this, you can really find out the various parameters of bulk density, packing density. So what is the essence of this optimization of aggregates? Packing density of combined aggregate with manufactured sand as aggregate is found to be more than the natural river sand for all the aggregates which were used to tested, and indicate that more paste is available for the aggregate combination when manufactured sand is used as fine aggregate. That means that there's a better packing density. So when the packing density is more, volume of paste required is less. So that when you are fixing the minimum paste content, you are left with generate more paste volume so that your workability and strength requirements are taken care. Aggregates from VSA crushers are found to be superior in comparison with aggregates from core and jaw crushers in respect of packing density. This is due to the method of production of this production resulting in well-graded chemically shaped aggregates. The packing density for VSA crushers are in the range of about 0.679 to 0.713. So how do you have to look into these figures? So let me explain. The concrete is about 1,000 liters. 1 cubic meter of concrete is about 1,000 liters. Suppose if we have about 700 liters of aggregates, remaining 300 liters is the paste content. So now you can determine how much paste content is required provided you know the packing density. So if the packing density is good and the volume of paste required is good, you can finally end up in a good concrete which gives you some requirements in the first stage, if it's a normal concrete, and in terms of that's a vertical stump. If it is a flowing concrete, we'll measure the stump in the horizontal direction. Then, if the concrete made is performing very well in first stage, then we need to look into its properties in hardened stage. So we test the concrete in the compression testing machine, and also the typical failures are shown in the figure where you should get only vertical cracks or inclined cracks, no horizontal cracks should come if the concrete is cast properly. Now, the very purpose of understanding the packing density or the properties of aggregates is to make a concrete which is durable, long-lasting. So, durability tests are also done in the laboratory, which will give some of the durable parameters such as water penetration tests, wherein we will come to know how dense the concrete is which you are made using the aggregates packing density or the aggregate parameters properties like that. So this water penetration test is nothing but dim water permeability test, wherein we apply the water pressure of about 5 bar pressure continuously for 3 days, 72 hours, and then we take the sample and find out the depth of water penetration, how much water has penetrated into the concrete. Normally, these values are limited by the project specifications. Some specifications say it shall not be more than 10 mm. Some specifications say it shall not be more than 15 mm. MORK specifies the water penetration value shall be limited to 25 mm. So we can measure only by splitting the cylinder. Another useful test in the durability point of view is the initial surface absorption test, which gives the surface characteristics of concrete, whether the surface is dense enough, whether it is sound enough, which will not absorb much water. So it's a surface absorption value we find out after 10 minutes, 30 minutes, 1 hour, and 2 hours. And then this is how the average the average and low values are specified here. So this is a test which we do. So now in the presentation, we'll follow 15 minutes. So this is a very simple test to know the surface characteristics of concrete. Another important test we conduct, especially for the concrete made in coastal areas, is rapid chloride penetration test, RCP2 test. RCP2 test is done to check the permeation of chloride ions into a concrete. How much, say 6 hours a simple test, we need to have this equipment to carry out this test. And this table given in ISTM 1202 gives the requirements. And if you have made a good concrete by good gradation of aggregates, good quality of aggregates, the permeability values can be as low as 1,000 to 2,000 or maybe less than 1,000 coulombs also. So this is a bin permeability. These are the typical values for water penetration test, rapid flow permeability test, initial surface absorption test, and water absorption is another simple test nowadays becoming more and more popular. The water absorption value will be if the concrete is very well compacted and having a good duration of aggregates. The water absorption can be less than 1%, but normally it won't be so less. In normal concrete, it will be at least around 2% or so. But this particular concrete was a high strength concrete, maybe because of that and this thing, high performance, we got such very low values. So water absorption is a very useful durability test which we do. So looking into all these things, the very purpose of studying the properties of aggregates, thereby which affect the properties of concrete in fresh stage, hardened stage, from the strength point of view, or from the durability point of view, in order to achieve durable concrete, meeting the requirements in both fresh and hardened stages, aggregates plays a very important role. Selection of aggregates and optimizing aggregate content in the total mix is crucial to achieve a durable concrete. So this is what I wanted to discuss with you, because you, all of you professionals must be following the testing aggregates on day-to-day basis in RMC plants, in QAQC laboratories, site laboratories. But the importance should be given to gradation of aggregates, blending of aggregates, shape of aggregates, then the source of aggregates, whether it is in a vertical shaft impact pressure or not. And again, finally, also you need to look into this M sign, what is the percentage passing through 75 micron, because this is very, very critical, very important. It increases the water demand, it increases the cement demand. So with this, I would like to conclude my lecture by telling, be safe from coronavirus infection, be smart and inform about yourself, be kind and support one another. Thank you very much for your kind attention. Thank you very much.